topic is power. Power is really just energy, but we're adding back time. And it's important because of things like this. So remember, we've been ignoring time. So the work has really just been like, okay, at some point it gets to this speed. In this case, 0 to 60 miles per hour in 3.4 seconds versus, does anyone even have these anymore? A 1999 Dodge Neon. I need to get like a more current car that people recognize. At 0 to 60 in 12 seconds, okay? So really fun times at the track. So power is really how quickly energy is transferred. And this ends up being really important for things like energy needs for your home, right? So when we talk about the energy grid, having power ratings on things really matters. Like time is an important thing. And what I mean by this is a light bulb. How long do you usually have a light bulb on?
Like 6 hours a day.
Yeah, so maybe like 6 hours a day, right? A toaster uses a lot more energy per time, right? It has a much different power. But if you're just talking about energy and you say, okay, well, a light bulb is, let's say, 6 watts and a toaster is thousands of watts, you might think that the toaster is the bigger issue. But because we have to account for time, power is the bigger issue, okay? So that means that the amount of time the light bulb's on, that gives you your total energy. So how much energy you use per time is a very important part of figuring out how we manage our energy systems, okay? So power is just how quickly energy is transferred. We mostly use this watts, and a watt is a joule per second, right? Energy is in joules. The time we usually use is seconds, so watts are just joules per second. Horsepower is a more archaic definition. You can transfer back and forth between horsepower and watts, but watts are a much better thing. You'll often see things written in kilowatts. Side note, kilowatt hours. What is that a unit of? Power or energy?
Energy.
Energy, because remember, power is energy over time. A kilowatt hour is energy over time times energy. We're back to energy. Why do we call it kilowatt hours? Well, it just makes the math easy to do when you're canceling the units so that people can calculate their own electric bills, okay? But the way we define power, it's the derivative of the energy of a system over time, okay? With respect to time. You can also define it as the derivative of work with respect to time, because remember, work is just a type of energy. It's usually just an external energy coming into the system. Here's a third definition that's less exciting, but it's just force times velocity. That comes up much less frequently, and it's a dot product. Power is in watts. A watt is a joule per second. Okay, cool. So we're going to try this example. Oh, 1 horsepower is 746 watts. There's like some interesting story behind horsepower, but I can't remember what it is. So I'm either going to like make something up, which is a lie, or I'll just look it up and tell you later. I think it definitely comes from the fact that we used to generate most of our usable power with horses and other animals. Back before, what? No, I didn't. No, that's true. Back before dogs were just pets, they often did a lot more work, like turning things, so they created their own energy. You can also use children to power your turbines, that's fun. It's a joke. Don't use children to power your turbines. But they have a lot of energy. You could just make them run in a circle for a while, then you could like power your whole house with and wear out your kids. It seems like a perfect solution, except they would refuse to do it by like day 2 or halfway through day 1. Okay, so I keep thinking about attaching their iPads to like an elliptical so that they have to like exercise to watch the iPads. I feel like this is a parenting hack that I need. So we have an elevator motor. It lifts a 1,000-kilogram elevator to a height of 100 meters. We want to know how much power is needed to do this. Oops, okay, well that's the answer. To do this at a constant speed. And why are we, whenever we see constant speed, what should we be thinking?
Zero acceleration.
Zero acceleration, right? So we're trying to make this simple by having zero acceleration, okay? So here's our elevator. Let's draw the elevator. So here's our y-axis. So the elevator goes from, let's say this is 0 to 100 meters. It's not a very good elevator, but you get the idea. Okay. What are the forces on the elevator?
MG.
Yeah, there's mg and then there's probably another one.
Yeah.
We'll call this F lift. And mg, yeah, it could probably be tension, but we'll just call it F lift. Since there's no acceleration,
0.
that means when we add up our net force, it should be 0, which means that F lift, I can't spell lift, is equal to mg, which means that we know F lift is 1,000 kilograms times 9.8 meters per second squared, which is 9,800 newtons. Okay, so if we want to figure out our power, remember, since this is a constant force and therefore constant work, do we need to do a derivative in this case? No, it's not going to matter. So it's just going to be work over time. So we say work divided by delta t. So delta work divided by delta t. I guess we don't need the delta, but is going to be force lift times d over delta t. So that's going to be 9,800 newtons times 100 meters divided by 50 seconds. And that's going to give us 19,600 watts or 19.6 kilowatts. So next time you're in an elevator, you can see if you can find the power somewhere on the elevator and decide if this is a reasonable amount of power for an elevator. Okay? Also, if you put people in it, it'll have a different mass. Any questions about that? Power is pretty straightforward, but it's an important concept when we get to circuits. Any quicker question? Okay, it's either A, B, C, or D.
Oh,
Huh. Okay. The answer is D.
Dang, that's crazy.
So maybe we should do the math. How do we figure this out? What's the formula here?
work over time.
Yeah, the power is gonna be the work over time. That's showing up, right? So that means force, so mg y over t. Okay, so in this case, we're gonna just call g 10 for the heck of it. So that's going to be 80 times 10 times 10 divided by 10. So what's that? It's 800. 800. 800 what?
Watts.
Watts. 80 times 10 times 10 divided by 8.
1,000 watts.
1,000 watts. 64 times 10 times 10 divided by 8.
Also 800.
Another 800 watts. Okay, so we know A and C are the same. That's good, because both A and D answers gave us A and C the same. And then the last one is going to be 80 times 10 times 20, 10 times 20 divided by 25. So 80 times 10 times 20 divided by 25.
Did you get the 10 from?
Gravity.
G is 10, yeah. It's like it's a really annoying amount of numbers. 160. It's in between. Does anybody know that one off the top of their head? Anyway, the answer is D.
I agree.
I'm gonna say it's smaller than 800.